In this video, we'll look at average value, and we'll also revisit the mean value theorem and learn how to apply that to integrals. The AP standard for today is CHA-4.B.1, and it says that the average value of a continuous function f over an interval a to b, and this is the formula that we're going to use for the average value. So make sure to write that formula in your notes. The average value is equal to 1 divided by b minus a times the integral from a to b of f of x dx. To calculate average value, we'll use the first fundamental theorem of calculus that we looked at in the last few videos. Using calculus to find the average value of something is a really powerful tool. Typically, if you want to find the average value of something, you have to add up a lot of different data points and then divide by how many data points there were. But by using this average value equation, this gives us another way to calculate the average value so that we don't need all of those individual data points. So here's an example of how to use the average value. Let's say we want to find the average value of f of x is equal to 5 minus x squared on the interval from 0 to 2. Here's a graph of what that looks like. It's just a parabola pointing downwards. The graph exists completely above the x-axis on the interval from 0 to 2. So here is our formula for average value. We need to substitute in values for a and b, and then substitute in our function f of x. A and b are the boundaries of the interval that we were given. So in this case, a is equal to 0 and b is equal to 2. If you substitute everything into the average value formula, we get 1 divided by 2 minus 0 times the integral from 0 to 2 of 5 minus x squared dx. Now we can use the first fundamental theorem of calculus. We want to find the antiderivative of the function 5 minus x squared. That antiderivative would be 5x minus 1/3 x cubed. Notice that I put a bracket around the function here. I did that for two reasons. One, it separates off the function from that coefficient out front, 1/2. And also by having a bracket, I can place my boundaries on the outside of the brackets to the right. And I don't have to draw a vertical bar like I showed you how to do in previous videos. Next step is we want to plug in those boundaries. I'm still keeping that 1/2 coefficient out front. Start by plugging in the upper boundary into all the x's. That would give us 5 times 2 minus 1/3 times 2 cubed. And then you want to subtract and plug in the bottom boundary into all the x's. Be sure to put a parentheses around everything where you plug in the bottom boundary. You want to make sure that you're subtracting everywhere that got that bottom boundary. Well, by plugging in a 0, the 5 times 0 goes to 0, and the negative 1/3 0 cubed goes to 0. This then simplifies to 1/2 times 10 minus 8/3. We can find a common denominator, and then our final answer is just 11/3. So this is the average value of the function over the interval from 0 to 2. And take note that that average value is actually a y value that we just calculated. So then where does f of x take on the average value? To figure that out, all you have to do is set your function f of x equal to the average value and then solve. So if we set f of x equal to AVF, that means that 5x squared would be equal to 11/3. All we need to do now is solve for x. If we find a common denominator, we can then combine the 5 and the negative 11/3 to be 4/3. And then take the square root of both sides to get the x by itself. So then I get a plus or minus 2 divided by the square root of 3. You can rationalize this answer if you want to, but I'm not worried about that. What I am worried about is the fact that we have a positive or a negative answer here, but our original interval just went from 0 to 2. Since the interval is from 0 to 2, the positive answer is the only legitimate one here. So x is equal to 2 divided by root 3 is our final answer. Okay, here is the mean value theorem for definite integrals. If f of x is continuous on the interval from a to b, then at some point c between a and b, f of c is equal to 1 divided by b minus a times the integral from a to b of f of x dx. So notice we're just setting f of c equal to the average value formula. So what this means is that the average value, which is the y value, will always occur somewhere between f of a and f of b, and that will occur at x is equal to c, which is between a and b. So this is the mean value theorem for integrals. F of c is equal to the average value. If we take the antiderivative of f of x and apply the first fundamental theorem of calculus, then our equation would look like this. So let's just pretend that we were looking at a higher order of a derivative for f and capital F. So then on the left we have f prime of c, and on the right we have little f of b and little f of a. We can then rearrange that formula like this, and notice that is the mean value theorem for derivatives. So the formula for the mean value theorem for integrals is really similar to the mean value theorem for derivatives. Okay, here's one last example. Let's say that we want to find the value of x that is guaranteed by the mean value theorem for integrals for f of x is equal to 4x minus x squared on the interval from 0 to 3. So start by using the mean value theorem formula. F of c is equal to 1 over b minus a times the integral from a to b of f of x dx. Put our function on the left, but substitute a c in for the x's. That would give us 4c minus c squared. And then on the right, we substitute in our a and our b, and then put our f of x inside of the integral. So now we need to evaluate that integral, turn that integral into a single number, and then try to solve for c. The antiderivative of 4x minus x squared is 2x squared minus 1/3 x cubed. And then put the boundaries from that integral, 0 to 3, on the outside of the right-hand bracket. We can then plug in the top boundary 3 in for the x inside of the 2x squared, and then also into the x for the negative 1/3 x cubed. What happens if we then plug the bottom boundary into the function? Well, 2 0 squared would be 0, and then negative 1/3 0 cubed would also be a 0. So by plugging in the bottom boundary, we're just going to get a 0. So then we just want to work on simplifying that parentheses. We get 1/3 times 18 minus 9. And then the right side just simplifies down to a 3. We have a squared term, the negative c squared. We have a linear term, 4c, and you have a constant term, the 3 on the right. So we would call this quadratic in form. If your function is quadratic in form, then you want to set it equal to 0 and factor. So moving everything over to the same side of the equal sign, and then also making it so that the c squared term is positive, we'll have c squared minus 4c plus 3 is equal to 0. We can now factor this to be c minus 3 times c minus 1 is equal to 0. And then just solve each of those parentheses for c. That gives us c equals 1 and 3. The final step here is we want to consider our answers, c is equal to 1 and c equals 3, and check to see if both of these are legitimate answers. The hypothesis for the mean value theorem for definite integrals said that f of x is a continuous function on AB, and that your point C is on AB. C on AB means that C has to be between AB. So we want to make sure that our answer for C is between A and B. The interval that we were given was from 0 to 3. So that C equals 3 is not between A and B. So we can discard 3 as an answer, and our final answer is just C is equal to 1.